partners at the Imaging Research Center. At CS3, we try to sponsor events and trainings like this one developed to support your research productivity and aid you in communicating your complex ideas. Our guest, Dr. Kieran Healy, has written a recent book titled Data Visualization that can help you do just this. A few housekeeping notes before we jump into today's session. First, please feel free to put questions in the chat throughout this afternoon's workshop, and we'll be sure to monitor them throughout. Second, this session will be recorded and the link will be sent out later this week. Third, 5 lucky attendees will receive a copy of Dr. Healy's book, Data Visualization. I have a copy here, a practical introduction. We'll be announcing the winners at the end of the session and then reaching out to get you your copy of the book. Finally, CS3 will be offering a 3-day data visualization workshop using Dr. Healy's book in January. So we'll send out details soon with respect to that. You might be interested on October 16th at 4:30 p.m. in the library gallery. Dr. Michael Fernandez, director of the Epicenter at the American Association for the Advancement of Science, will be giving a talk on evidence-based policymaking. To learn about these and many other CS3 planned events this semester, please visit our website, socialscience.umbc.edu, and subscribe to our events calendar. We're also on LinkedIn, Facebook, X, and Instagram. Finally, you can tune into our podcast, Retrieving the Social Sciences, which you can find on Spotify, Apple, or Amazon. Again, thank you for being here. I will turn things over to Dr. Kieran Healy. Dr. Healy is a professor of sociology at Duke University, as well as a member of the Keenan Institute for Ethics and a regular visitor to the Research School in Social Sciences at the Australian National University. Dr. Healy's research focuses on the social organization of exchange in human blood and organs, cultural goods, software, and ideas. He also studies the moral order of market society and the models and measurements of social classification. Important for our purposes, he is an expert on data visualization and being able to communicate complex ideas honestly and through stunning visualizations. So please join me in welcoming Dr. Kieran Healy.
Thank you very much, Eric, for the kind introduction. Let me just set up my sharing thing here. And thank you all for attending. It's a pleasure to be here. There we go. Right, you should see me up here. And so now I can switch over to my slide here. And just need to get myself organized. There we go. All right. So thanks again for coming, and hopefully this will be a useful talk for people. The title, as you can see, is Honest Data Visualization. I was thinking about this topic, thinking about presenting kind of over WebEx or in an environment like this, a Zoom-like environment, something we all got extremely used to, or have gotten all extremely used to over the last few years. And with a laptop and some free software and a cup of coffee, back when we were all trapped at home, we can all examine what ought to seem like a staggering quantity of data, just kind of at our kitchen tables, so to speak, right? And so here, for example, is a picture showing what driving patterns in the United States and many other countries look like in 2020 as lockdown happened. These are driving trends in cities around the world from the first 18 months of the pandemic. And the idea is that Apple and Google and other, those are the two main ones, but they released this public data that was derived from their mapping software and driving directions, and presented it to people to analyze, with the idea that things that could help with the battle against COVID. And the way that they did it, this is Apple's data, was that they indexed things to 100 from January of 2020, and then what you saw was daily data for each city reflecting either the activity above the original index or below it. And what we see in all of these cities is life going on as normal. The little bars you see are kind of the weekly pulses of people commuting to work. Here's one for Baltimore. The little pump, 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 and then here's the initial lockdown, which went on for to different extents and for longer periods of time in different parts of the world, and then eventually, sort of everyday life started to kind of reassert itself. When we work with data like this, and when we can present with data on this scale, I mean, this kind of thing doesn't count as like big data anymore. It's, even though there's several million rows in the data, like you can do it on your laptop, as I say, in your kitchen. And when people look at data of this kind, often, or presentations or analyses of it, there's often this kind of critique that, reducing everything in numbers in this way kind of inures you to the social reality underneath, the lives, the suffering that people were going through, the disaster that was COVID, and just the details and the fine grain of human experience. And there's something to that critique, but I also think it can be a little bit lazy. And in my experience, kind of working with data of this kind is a kind of constant exercise in humility, in the sense that you're constantly being reminded of what the data can and can't tell you, and what you can and can't see. And you're always trying to kind of do your best with it as you go, and working with it on this scale remains a kind of remarkable thing to me. Like when I was a graduate student, and distressingly a long time ago, I spent a week in the library hand transcribing stuff from OECD manuals so that I could put them into a bar graph like this. And so things have really changed, but the fundamental problems that we face when looking at these data of this kind and trying to represent it are the same as they've always been. We want to understand our data and display it intelligently. We want to do it reproducibly, something that's become increasingly important as social science has changed over the last 30 years. And we want to do it honestly. And I'll talk in this talk about kind of what that means. The broad theme of the talk, the sort of way that I think about this in general, is that I want to emphasize the kind of continuity that there exists between kind of representing data visually, drawing data visualizations, and any other kind of systematic investigation of data. Data visualization is not special in the sense that it doesn't sort of give you some magic ability to see things as they really are, and to uncover things that are literally impossible to see any other way. It is an extremely useful tool. But there's a reason that we have other methods, and there's a reason that we have statistics and archival work and interview data, and people doing those kinds of, working in those kinds of modalities with the data face exactly the same kind of problems. They too want to represent their data honestly and intelligently, and data visualization is not special. And I say this because because visualization has our ability to do it on increasingly large quantities of data has become much more extensive over the last 20 years in particular. There's a pitch that often happens with kind of people who like doing data viz like me, that tends to oversell the differences and also to overclaim for what it can do for you. And so there's a story, how you can really see how things are, that you can tell stories with the data. Well, you can tell stories with the pictures. You can tell stories with all kinds of data, and they can be good or bad, or true or not. And so, as I say, when we're working with visualizations and thinking about how to do them properly, the problems that we face are not that different, really not any different, except in their details from the problems we face doing any kind of data analysis in a reproducible, intelligent, and honest manner. With that in mind, it is true that, like any particular way of working with data, visualizing it presents its own kind of challenges that we have to think about carefully and work with. And sort of the story here, to begin with, is that seeing is not as simple as it looks. Right? Is the idea. This is a picture of the one representation of the color space that people can see, and when we think about representing data visually, we need to think in a careful way about what it is that we are doing and how it is that we should do it effectively. Here's an example, just starting from the kind of level of perception. I promise I'm not I'm not cheating here. These are two perfectly geometrical circles, and I'm going to sort of run them here for a second. Let me get this somewhat distressing effect, slightly trippy. Not that I know anything about that. Hopefully these effects are kind of coming through on as you watch. One of the things that we'll talk about is the way that we have to think carefully about who it is and under what circumstances people are looking at things. When I present this stuff, sometimes I'm in a big room with a huge screen that isn't very well lit, and things get kind of washed out. Other times people are in front of their laptops, so I'm never quite sure what people are seeing. But these kinds of visual effects raise this question of kind of, well, what is it that we're looking at, and what is the process of visualization, and how does it affect our representation of data? And so the questions that we're going to be concerned with, when I teach courses or give talks on this stuff, I try to address kind of these questions, which is sort of, how should we see, and where should we look, and when we look, what is visible? Is that, yeah, it's going up the right way. It's flipped around on the other side, but not on this one. What is visible? Today we'll focus mostly on the first one, but again, I don't want to lose sight of the fact that, like, just as with any other form of data analysis, with any other form of systematic investigation of the world, the kind of data that's available to collect, the kind of things that get the decisions that we make when we include things or leave things out, what we can and can't see, literally in this case, those kinds of questions are always with us right the way through. So when we look at visualization, it's worth thinking about kind of what it is that we're doing. And so if I'm sitting at my computer and I've got some data that I'm working with, and what I want to make with that data is some nice graphs to show people, the question is, like, what is it exactly in principle that I take myself to be doing under these circumstances? And kind of the answer is that what I'm doing is I'm taking the data and I'm trying to find some mapping or some encoding, some link in a sort of quite strong, functional sense between that there's a connection and a sort of invisible line that leads from the data to the marks on the page or the dots on the screen, and that link kind of faithfully represents in some sense the contents of my data in terms of the things that you can see, the lines on the page, the dots on a screen, the colors that they have, and so on. That each of those features that you see when you're looking at a graph represents, in some faithful and accurate, honest manner, and hopefully enlightening kind of manner, the contents of the data that I'm trying to show. And that process of encoding is the challenge of representing data in an effective and honest manner. And so when you, as the audience, are watching me or someone like me give a talk, or when you're giving a talk yourself and you're showing an audience the graph that you're working with, well, then what you want to have happen as the speaker is for the audience to be able, in their minds, so to speak, to decode the contents of that graph and get an accurate sense of what the original underlying data is and what it was saying as they look at it, that they can, so that we can not only just encode the data, but that it can be decoded effectively and in a sort of elegant and ideally efficient and enlightening manner. I mean, when it comes to a table of data, if we encrypt it, that's also a mapping, and that gives a different representation of the data, but you can't decode it without a special key. Visualizing data, we want to make that key as easy as possible to access, ideally with as low a bar for the audience that we're talking to as is necessary to get the job done. And in that task, some graphs are better than others. There's better ways to do it, and there's worse ways to do it. And so making and interpreting a data visualization is kind of partly a matter of knowing some concepts or ideas, and it's partly a matter of working with your data honestly, and it's partly a matter of knowing how to handle the tools that you're working with in order to do a good job of working with that encoding. And our tools aren't always up to the job. Many of the common tools that we use are not very good at doing the thing that we want. And so here's a case of a 3D column chart, the kind that you often see in presentations. Business people love these especially, but you see them all over the place. And this is made in Excel. And you can see right away that columns A, B, and C, and D here, the relative sizes of the columns are easy to see, and you can tell that A is smaller than B and so on. If you had to bet your life on how high the actual bars are, like this height as opposed to this height, the question is, well, what would you guess the numbers are? And it seems like the graph is trying to help you. It's got a scale here. These lines kind of helpfully go around, and you can start to sort of say, well, is it like kind of like this? They go over like that, maybe. That's how people tend to look at sort of graphs like this. And unfortunately, that's not how these data are encoded, right? This is just kind of 1, 2, 3, and 4. And the reason that it looks this way is because of the sort of quasi-isometric perspective that Excel has chosen to draw this data, draw these data by default. And there are many, many examples kind of along those lines. It's traditional in talks like this to give a kind of parade of horribles. I mostly won't do that. We'll have a couple of quick examples, and we'll move on to the good stuff. But we can see that we can get this more or less right or more or less wrong. There are 3 main reasons, let's say, that things go bad, that I'll dwell on, or I'll talk about in kind of increasing levels of detail. The first is graphs are bad because they're just in bad taste. They're badly designed and aesthetically offensive. They look terrible. The second is that they're showing bad data in some sense, that regardless of how good the graph is in terms of its purely kind of design or aesthetic characteristics, it's not doing what it's representing is in some sense misleading. And the third and maybe most interesting category is that they're perceptually bad, that even when we're trying to do the right thing, and even when we have what you might think of as strictly aesthetic high standards, there's something perceptually off about the graph that makes it difficult to interpret. When it comes to taste, the arbiter here is Edward Tufte, who in his famous book, The Visual Display of Quantitative Information, who really kind of pushed this line that graphs needed to be devoid of junk, that they needed to be simplified, that they needed to maximize, in his terms, the data to ink ratio in graphs. And what he had in mind, for example, is something like this. This is a graph I made in Keynote. It's nice representation of life expectancy. We've got some pleasing wood grain textures here. We've got some shadows being cast. We have papyrus, of course, everybody's favorite off-brand herbal tea font. And Tufte's point here is that there are only 5 numbers being shown in this graph, and it's quite difficult to tell what they are just by looking. And we could simplify it one way, for example, just down to an ordinary bar chart that showed this data much more effectively and in a much simpler way. That's a very good policy. Maximizing the data to ink ratio is a good idea. It has its limits, though, and we can sort of take away too much of the scaffolding that people need. Is one problem in order to understand these visualizations. The second one, though, is that we can have charts that do look good, that meet these criteria, but that are still kind of misleading. They don't have any of the chart junk that Tufte identified, but they are in some sense kind of off. So this is from the New York Times from a few years ago, from a paper in the Journal of Democracy by Yasha Monk and Roberto Stefanfoa. And this graph, has many nice design features. People at the New York Times do a very good job. They redrew the graph that was in the original paper. And it seems to show, that the percentage of people who say it's essential to live in a democracy is declining precipitously. If not directly over time, it does say decade of birth rather than kind of time surveyed. This is not like a longitudinal study. It's more like people who were born in this decade at the time they were surveyed. The graph has several nice design features. The countries are ordered in terms of their kind of average value from high to low across the graph, which is nice. Instead of being presented alphabetically, we have a nice visual rhythm from left to right, showing us sort of progression. We've got a measure of uncertainty, a little explanation about what that is. We have a lot of efficiency in terms of the labeling. We say 1930s and 1980s here, but then 30s and 80s here. We don't need to label every single tick on our x-axis. And we see from 0 up to 100% here. When political scientists looked at this, including Eric Wooten, they knew that this came from the World Values Survey, and it looks like what's being asked is it looked like a reasonable inference for this graph is to sort of say what people were asked is, do you think it's essential to live in a democracy? Yes or no? And this is the percentage of people who answered yes. And you can see it sort of declining as people get younger. But that's not what the original question was. It was on a scale of 1 to 10, how important is it to you to live in a democracy? And the same data are here, declining in the same way. It's just, and so there may well be a real thing happening here. And this is an important question. One of the reasons I choose this example is because it's a question that we care about. But I do think it's reasonable to think that they wouldn't have gotten into the Times, that this had been the original graph in the paper. I want to emphasize, by the way, that this is not a matter, something I'll come back to a bit later. It's not because the x-axis doesn't, or the y-axis doesn't go to 0, right? And here we have a scale of 1 to 10, and here we have a scale of 0% to 100%, right? It's because the data have been sliced in a way to make the effect sort of more dramatic. So we need to watch out for that kind of thing. If our data is bad, or if we're trying to lean on it, which is a pressure that researchers experience both sort of explicitly and implicitly. Human beings are very good at detecting patterns, and our job as data analysts is to find those patterns. And if we really want to find them, we'll find them, whether they're there or not. So the third category of ways things can go bad is in terms of perception, and this is much more at the kind of ground level of what happens when we look at things. And it's been clear to psychologists since the late 19th century that the human visual system is a pretty complex entity that doesn't work in ways that we expect. This is the Hermann Grid effect, or Hermann Grid illusion, that was first sort of noted in the late 19th century. The idea here is that if it's working as expected, the idea here is that you can see these kind of ghostly black dots appear at the intersections, but only in the cases where you're not directly looking at it. If you look directly at a particular intersection, then the dot will go away. And so this was one of the earliest indications that the visual system was really doing a lot of work, like was really an active process. You have this kind of naive idea, if you like, of that, what happens when I look at things is that light comes in through my eyes, and it goes to the back of my eyes into my optic nerve, and it goes into my brain, and inside my brain there's a person who looks like a tiny version of me sitting in an armchair, looking at a movie screen of what's happening outside in the world. And it's like, well, that's not how perception works. And all of the early kind of efforts to sort of figure out what it was that our visual system was doing would bring this out. This is called a Fraser column illusion, where it looks like, because of the alternating pattern of lines here, it looks like these lines are diverging, but also converging in ways that they can't really be together, like this. But in fact, it's just a repeating pattern. The kind of illusion happens kind of here with this pattern. And there are many such examples. Well, how might this kind of affect us in terms of the kind of data visualizations that we look at? One thing, we can come up with an example here with what are called Mach bands. So here we have a series of grayscale images from dark to light, and we can see that there is a progressive, we go from black at the top to kind of lighter gray at the bottom, and we can see the differences between them. But if we just shift them together so that the borders are touching, well, then now I think you'll see that the apparent contrast between the grays appears stronger in the case where the bands are touching. It's easier to see the contrast just in virtue of them sharing a border. And that's because the human eye is not a light meter, right? It's not good. It's not particularly good at detecting absolute levels of brightness in a scene. Instead, we're much better at detecting contrasts and borders. And this is the kind of thing that can come up. Here's another example, right? These are 4 identical shades of these rectangles, all of the same shade of gray. But if I put a gradient behind them, well, then the ones on the right suddenly look much lighter than the ones on the left. If the human eye was a light meter, we wouldn't experience that kind of contrast. And that's why professional photographers have those things, right? They have little light meters that they hold up to see how much ambient light there actually is in a room, because they know, or where they're shooting, because they know that they're not good judges themselves of how much light there is. Perhaps a particularly spectacular example of this is Edward Aleson's checkerboard illusion. The idea here is that this square is the same shade of gray as this square. which really doesn't seem possible. And this is supposed to sort of convince you that it does. I find that people don't believe it because they think it must be different. But so let me run a little animation where I promise I'm not cheating. I'm just going to cover up the areas. And as the information in the scene goes away, you'll start to see quite late, actually, that the two shades of gray are in fact the same. It doesn't seem like they could be, but they are. And the reason that they are is, as I say, the human eye is not a light meter. What it's doing, so to speak, it's easy to slip into this kind of anthropomorphic language of like what it's doing and what it wants. But what it's evolved to do is to assess scenes and see what objects are actually in them as best, so you don't get eaten, or maybe you find something to eat in the long term. And so the question, so to speak, that the eye is asking is this a dark object in the light? Is this a light object in a shadow? And it uses contextual information to make those sort of decisions, so to speak. And in this case, the shadow apparently being cast by the cylinder and the alternating pattern of checks sort of pushes you in that direction. Now, I think about this kind of effect. Sometimes cognitive scientists like to call these visual effects rather than illusions, because if you look at if you watch a card trick and or somebody doing sleight of hand, and a close-up sleight of hand magician, and you come to understand what it is that they're doing, then you can see the trick, so to speak. You can see through it, and you know what's happening. But in these cases, you could know all there is to know about the human visual system and its information processing, but you would still, as a human being, not be able to not have this happen. So this is not a kind of trick that you can see through, so to speak. It's just a fact about how the human visual system works. And so in that sense, they're not illusions, right? This is just what you see. And it's misleading, but it's because of how your visual system works. And so how might this come up? Or how might these kinds of issues come up in terms of the practical business of making data visualizations? Well, here's an example from a nice paper in Nature Methods, a good paper. And again, to be fair to the authors here, what they are interested in this paper is the contrast in sample 1 here from the other, mostly sample 1 and 2 from the other samples. And they present this heat map, a kind of tool we use all the time. And you can see the blues pretty well. It's worth asking, though, if you were to look at this, and again, if you were trying to sort of decode what's in the data, if you were to ask yourself, what other squares on this heat map are the same shade of light brown as this one that I've highlighted? You can give yourself a moment to sort of think about which ones you would pick. It's like, well, you might not pick this one, for example, even though it is, or this one, or this one, or this one, right? They're all the same. And the reason they're all the reason that it's hard to tell, let me show you that again, is because of the relative colors of the borders. This is the sort of Mach band effect, where the contrast appears higher because one is a light square surrounded by dark ones, and one is a dark square surrounded broadly by light ones. And so as a result, we interpret the relative differences in different ways, even at the level of the graph itself. And there are many such effects, even in this kind of small space, using a good palette and so on. For example, here's a stack column chart, again, another kind of chart that people like to, a graph that people like to make. And again, there's no junk in Tufte's sense in this chart. This is well designed. Like the data to ink ratio is very high, and there's no additional crud in here to distract us. But it's easy to see, while it's easy to see, for example, the relative differences in value in series 1 here, across the bottom, comparing this one, for example, to this one, or this one to this one. If I were to ask you kind of how much bigger or smaller is this set of sales from this one, well, that's a much harder task to accomplish. And the reason it's harder is because we're not very good at comparing the relative lengths of things where they don't share a baseline, right? Where they're not all sitting on the same ground, so to speak. It's easy for when they're all in a line, but not otherwise. We can simplify this even more. This is from a chart by William Cleveland. Cleveland in the 1980s, as an engineer and software programmer, did a lot of the early work experimentally to kind of establish these effects, just asking people to make these estimates and figuring out, on average, how wrong they were or how close they got. And so again, a junk-free chart. If what mattered was the relative heights of the bars, it's much more difficult. It's quite difficult to tell. If they were all sitting down on the y-axis, you could tell instantly. You have no trouble. And these things can come out in quite subtle ways, right? So here's another example from Cleveland. Here with these, these two series look like they're converging over time, right? You get the sense that if they continued up, to the values of 10 or 12 or something further out of the right y-axis or x-axis, that the y-axis they would either join or cross even. But that's actually just purely an artifact of the aspect ratio of the graph. And if we stretch it out, we make it more like a widescreen view, we see that these two series, or it's the same data, the two series are the same distance apart and will never converge. The reason this happens, by the way, is because when we look at sort of these things, it's easy to see here that the distance we're looking at is this, right? This is the comparison that we're making. But when we get up here, we tend to look at this distance, like at an angle, rather than this distance, which is what we should be doing, and that's what makes it look like they're converging. So that the relevant vertical distance doesn't change; it just looks like it does. So this is a good thing in the sort of you want to make things look like they're changing really rapidly and in crisis. Then just compress the y-axis of your chart, and it's like, oh my god, it's chaos. So you want to make it look like stuff is happening at a gentle pace. Just stretch out the x-axis. And so this is the root of the example of why it is that like database people don't like pie charts. I'm contractually obligated to have a crack at pie charts, but this is why, right? This is the same data. This is also from Cleveland, and these values are all the same as the ones here, but it's immediately obvious what the relative values are in this case, because we're just much better at decoding lengths from a fixed baseline than we are at decoding angles and relative areas. And so when it comes to sort of presenting data, this is the sort of thing we have to worry about. So with that sort of whole family of perceptual issues that we have in mind, and we can learn kind of more about them. Sometimes we use them to our advantage, right? It's not like these are things that we always have to avoid. It's more like they're just features of how our visual system works, in the same way that we can't see infrared or ultraviolet, so there's no point in using those colors in a graph. Like, we just have to work with the fact that we need to take advantage of the physical facts about our perception and our cognition as we're designing graphs that faithfully decode or can be faithfully decoded by the typical viewer. And so this connects then to the question of honesty and good judgment, because we have to ask ourselves, like, what is it that we have to do as a matter of routine or as a matter of policy? How should we think about the question of presenting data in an effective and honest way? So to return to a kind of old chestnut on this front with baselines on the x or y axis, I showed you this version of our life expectancy by continent chart a little while ago. It's a good graph. You can see that we start here at 0 and we go up to 55 or whatever it is and come out to 70 in these cases. So that's one way to represent this data. We could also show it, and in fact, by default, most statistical programs, visualization programs, would show it sort of like this, where instead of going all the way down to 0, we use the range of the data to define the range of the x-axis in this case, or the y-axis if it was flipped around. By the way, just as a pro tip, if you have categorical variables, put them on the y-axis. Don't put them on the x-axis. You can treat it much more like a table, and things can be much more compact, and people read them from top to bottom. People are always figuring out ways to, how do I get this thing at an angle on the x-axis to label my countries or whatever it is? Put them on the y-axis. And so the charge of dishonesty here amongst, if you show this graph to you put it out on social media, people will be like, oh, you're lying with statistics, you're or lying with graphs. The baseline should go to 0. The trouble is, the response is, look, that there's no country in the world or no continent in the world where life expectancy at birth is 0, or is 5. And what we're interested in is kind of the actual range in the data. And so really what we're saying here is not so much that there's like an iron rule, but we have to think about who is our audience, right? And what are we trying to show them? And what can we assume that they already know? And so at one level, audiences can be skeptical because well-designed graphs have a kind of rhetoric, a visual rhetoric of plausibility all of their own. And then people know that before they might have been taken advantage of by a seemingly well-designed graph that had like a little a quirk in it. And so if your audience is expecting to see a zero baseline, well, maybe it's worth showing it to them. Here's some more COVID data from looking at 2020. Here we're using the 5-year weekly deaths for the 5 previous years to sort of form the implicit baseline of the graph, and showing then the immense kind of event that that COVID was. Again, nobody believes, right, that in the United States in any given week, nobody dies. And so you can reasonably ask, well, isn't this just wasting space? We could instead show it this way. And if we were talking to an audience of demographers or social scientists, I think that would be a reasonable way to present the data. And I do think in general, most of the time what we're looking to do is to present data in that way. But it's not always the case that our audience kind of shares those assumptions. And so we don't want to kind of have you must always do this. It's not, there's no iron rule that we should follow either way. There are weak conventions, like if you're using a bar chart, you should probably bring it down to whatever the relevant zero is. And if you're using a dot chart, then things are a little easier. But there's no kind of iron rule. You always have to consider, what am I trying to say and who am I saying it to? And what do I want them to kind of take away from it? And because things can get sort of silly if you push it, right? So this is real data from mean daily global sea surface temperatures over the last 40 years or so. But I just put the zero baseline on the graph after somebody complained to me on social media that I hadn't. And so this is in Kelvin, so we'll go all the way down to absolute zero. And so you can see there's nothing to worry about in terms of global climate change. I'm glad we sorted that out. So on the one hand, what we are doing in these cases is, we want to emphasize the virtues as goals of clarity in communication, of honesty, and of truth as we're presenting things. All of those things are true. All of those things are things we should aim for. But then again, in each case, what is clear depends in part on the context, who it is that we are speaking to, and what is we can assume. And by the same token, the techniques that we're using have conventions associated with them that people need to understand when it comes to decoding our graphs. And so even what we think of as kind of the most basic sorts of scatter plots or bar charts, you need to learn how to read those. And a surprising number of people, do not, or need to sort of have things explained in a way that they can sort of follow along and help trust you. And similarly, when it comes to truth, we have to ask sort of, not just is it strictly speaking the case, but what will be the meaning of how will this be interpreted by the audience that I'm working with. And this kind of stuff comes up all the time. I mean, just a few weeks ago, during the eclipse, I don't know if any of you got up to see it. I didn't. I was stuck here in North Carolina, and so I was interested in just looking at some of the data that's available for it. And the National Oceanic and Atmospheric Administration produces a tremendous amount of climate monitoring and satellite data for North America and for the planet as a whole. It's a really amazing resource. And one of the things that they have is data feeds updated every hour from the Goes East and Goes West satellites, which are 2 geostationary satellites. They're the places that pretty much all of your satellite weather data for North America comes from. And so I went and wrote a little R script to grab the hourly data over the course of the day of the eclipse and made a little animation of it sort of, together. And so this is like every hour over the course of the day. It's pretty nice. You can just sort of see the path of totality passing over the US and time passing, as the Earth rotates there, you can see the shadow of night sort of approaching South America by the end. Now, when I wrote this up and I kind of put it on my website, social media or whatever, and it got picked up and it ended up on the front page of Hacker News, which, if you don't know what that is, that's great for you. Don't find out. But it got a lot of attention. And in the comments, immediately was the question, is that fake? And which is, of course, like everything is fake online. But the question is, well, why is the night sky showing clouds as bright white? Because it should be dark, right? And how would that even work? Now, this is like a reasonable question. Obviously, I don't like the framing, like, is this fake or what? But it is, in fact, a perfectly reasonable question. And when you just drop an animation like this out into the world, it's going to arrive to people who have no context. They don't know who made it, who I am, where this came from, even if it's attributed. And so, and these data are in fact a composite. When Goes East and Goes West, generates these data, it's not just there's not like an iPhone camera up there taking a picture. They take pictures across like 12 or 14 different bands of the light spectrum, and then they stitch them together. And for the nighttime stuff, they use a composite of the visible bands, and then infrared, and which preserves the clouds as white. And so that's just their convention. But again, if you don't know that, or the image gets detached, well then it's reasonable to ask, is this real? So we need to be aware all the time of who it is that we're speaking to and what we can expect them to know. And that's true for social scientific work, for all kinds of visualization, because when we're making visualizations, what we're trying to do is communicate something to people, and what they know is going to vary. So when advocates of data visualization present their stuff, they often present like the most spectacular things that they can do. Like, look at this. And again, I'm contractually obligated here to show you Pierre Menard's Napoleon's Retreat from Moscow, which is popularized by Tufte again as possibly the greatest statistical graphic ever made. It's great. I mean, if you haven't seen it before, it shows the size of Napoleon's army as they march across Poland into Moscow and then retreat, and that and you have the weather and the time and the number of people who are killed and so on. Virtually nothing that we make, and including virtually nothing that Menard himself did over the course of an illustrious career as an information designer and engineer, looks like this. That this is not a standard graphic. Instead, almost all the stuff we do are just workhorses, right? We have regular workhorses, the humble histogram, or the scatter plot, or the Cleveland dot plot. But these are extremely flexible and powerful devices to help us, present information in a clear and comprehensible way. And they can be extended in ways that can be built up to something sort of a little more. But most of the work we do is just kind of, here are the simple plots that show the information in a direct way. We can extend our Cleveland dot plot to something that's conceptually almost an identical plot, but is now showing kind of point estimates for a model together with a confidence interval or some similar kind of confidence range around them. And with modern software, like with R, we can extend this to show kind of a whole assembly of models, let's say, in this case, or a whole assembly of cases or predicted values for different conditions in our model. So once we start to kind of build up from the simple case, we really can do quite complicated things. And the same is true of things like scatter plots or lines, right? This is just a scatter plot, and then also a couple of trend lines or estimate, quantile regression lines superimposed on top of them and then split into two. But you can see we can make things a little more complicated in a way that we end up, if we think about it carefully, our workhorses can do a great deal, right? And they can really do a lot for us. But conceptually, they're not complicated. And so here, for example, this is not really meant for a slide, it's a poster, but it's, again, all-cause mortality from COVID in the United States, where we have a kind of league table of areas covered by the CDC and with New York City at the top, using as a baseline the average number of deaths in each area, and then the effects of COVID in 2020. And we can just sort of see both any particular country. We have a simple confidence range. We see where the United States is, that we highlight in the middle, and we go all the way down to the end. We see things get, it goes everywhere. So that's how our kind of workhorses become show ponies, so to speak. This thing is on the wall behind me. Where again, what we're doing is taking what is in essence a fairly simple graph. It's just a heat map. But here we have, this is the demography of mortality in France over a 200-year period. So every square on the graph, we have time on the x-axis in years and age on the y-axis in years. And so every square then is a kind of particular mortality rate for that year at that age. And we can average over the whole of the time series to show where the where mortality rates kind of really pop out as being particularly high or low. And so, for example, we can see World War I for men here with a sharp cutoff for enlistment, World War II at the beginning and when France is occupied, and after kind of mess here. We can see the pandemic here for women and men, like a scar across the whole age distribution. And we can see earlier examples of cholera epidemics associated with wars that affect everybody. Also things like working age and maternal mortality, child mortality declining, and so on. So quite a lot of data packed in this case. But what we're doing, as I say, as we move around this graph, we can sort of investigate any particular pixel. But the result is that we can explain sort of, look, here's what each individual piece means, and now you can see what the larger pattern is. And so in terms of kind of strategies for your own visualizations, you can think of this, you know, as a generic sort of sequence where you layer information or data, you highlight the things that you care about or want to draw attention to, and you repeat design elements as you go in your data set. And there's lots of different ways in your visualization, and there's lots of different ways to do that, right? And so here we're making a comparison across 3 different settings. We arrange the panels so that they are ordered in a way that is comprehensible. And then once we've established that for 1, we can show 3. And once we've established that sort of comparison for 3, we can show another set that operates in the same way, right? We layer, highlight, and repeat the differences. The same goes for an example of our COVID plot, where we're highlighting the 2020 year in particular, in one case, and that can be extended to sort of small multiples, right, where we are doing the same layer, highlight, repeat strategy for many cases. As a final example, we can do this as well in sort of fun ways now with animation, for example, right? And so here we'll go back to our sea surface data. We've got millions and millions. We've got about 2 million data points a day for 40 years for the whole world that we're aggregating in this graph. And so we can just sort of set it running, where we're looking at daily global sea surface temperature with the years ticking by in the top right there. I find, by the way, when I run these animations, one risk of these animations is that I can say literally anything to the audience while they're watching it, and they're like, I'm watching the movie. But you can see, right, that you establish what the trend is, you establish what the pattern is, and then as time changes, as time passes, you start to see kind of where the trend goes around now. You'll start to see things get a little out of hand, so that this is when the climatologists start to kind of really get a little concerned. There we go. And this data goes up to, I think, the middle of March of this year. I should update it. You can just download it for free, process it, and come out the other side. And so here we go. It was this year and last year that the North Atlantic in particular was out of sync. So there's 2023 and here's 2024. So that's an effective way to present your data in an honest manner. And it's for that reason, that I think, right, that I'm committed to the view that data visualization really is a terrific tool for discovery in your own work, and for persuasion and argument and presentation of that work. It's just one tool amongst many, right? There's lots of tools that we have and there's a reason that we have them. And so when we're taking advantage of data visualizations, they don't replace the other methods that we have, they assist us. And in particular, the tools that we have, no matter how high our production values are, and no matter how flashy our methods are, the tools you have cannot magically make you honest or error-free or right. They can only help you in that way, but there's no kind of sense in which the tools themselves or the techniques themselves can make you honest. We're living in an era now of, high production quality, high value, and quite lucrative high profile science, let's say. And if a researcher isn't being honest, then no set of tools, can make them that way. So what we want to do is to take advantage, if we have a set of data that we honestly want to work with, and we're trying to discover patterns in it, well, then data visualization can help you find the right answers, or find answers that stand up to the best methods of scrutiny that you have, and help you communicate them to other people in an effective way. So thank you very much for your time.
Great, and let me say thank you, Dr. Healy. This was a wonderful, wonderful visualization presentation, both in terms of the narrative, but of course all the visuals that you had to display. I want to make sure we open it up to questions, and just to kind of lead things off. So feel free to either type it or raise your hand. I'll kind of lead off with one question, and in recognizing that really we have students and faculty from across not only the College of Arts, Humanities, and Social Sciences, but other colleges as well. So we have psychologists and public policy scholars and econ and GES here today. Thinking about the fact that many of us also use different tools to try to visualize our data, whether that be Excel or Stata or SPSS or R. How important is it to actually try to customize the tools? I know your book obviously is focused on R. If you are to use the default settings in many cases when trying to represent data, does it tend to lead you astray? And do you have any recommendations other than maybe learn R? So.
Yeah, I don't. I'm quite sort of small c Catholic about the toolkits people use. The reason I use R myself is partly just a matter of historical accident, although it has turned out that it's extremely effective. The ggplot toolkit is really, really good. So it's not required that you should learn any particular toolkit. It is true though that the defaults for some sort of toolkits are not as helpful or as good as others. There's been a lot of improvement right across the board as many tool sets have kind of converged on the lessons of people like Cleveland and other researchers have really been absorbed by the providers of many different kind of toolkits. And so you see it in Python, you see it in Excel, in Stata, and elsewhere. The most important thing is using the tools to kind of implement the principles that I've been talking about. And if your tool does that, then the most important thing after that is just to get your own work done, right? And don't spend all day kind of tweaking things in order to get it just right. So Stata has improved a lot over the last few years. ggplot is kind of, in my view, is the sort of best toolkit where the defaults are just very, very good. Several Python toolkits are also good. So you can do good work across all of these settings. Some things like Excel, you might have to work a little harder to kind of keep it simple, so to speak. But that's what you should, but good work is possible and within reach across all of these tools. The main differentiator a lot of the time is not just kind of what you can do with the limits, but also sort of how easy it is to do work that's reproducible, which historically has been very difficult for visualization in particular, because it's all about sort of, I'm moving this over here with my mouse, or I'm selecting this. And so one of the real advantages of programmatic toolkits is that you can draw the thing in a way that can be replicated on slightly different data rather than have to do everything all over again.
Excellent, thank you. And do others have questions? Let me certainly open it up to the broader group.
I don't know if you can see, I have my hand raised, but I imagine.
Oh, I'm sorry, I could not see it. No,
I kind of feel it because you're just seeing a row of whoever you have looking at the time. That was a wonderful talk. Thank you so much for that. I just want to say I really enjoyed it. I love what you stressed. I'm thinking about the visualization that is on the wall behind you, the one that looks at mortality since 1816. I can't remember where I did see that when it came out. Was that in the Times, or I can't remember where that was? But
so I drew the original one, and then I'm going to sadly forget his name. The Financial Times guy redrew it, a version of it for the UK,
brilliant.
And it appeared there. Yeah.
I teach visualization. It just totally caught my. I just thought it was a brilliant visualization. So well done. And what I want to ask you is about something that I think that graph really does beautifully, and And it's to understand what makes a good data visualization a great data visualization. And I'm wondering how this plays with you. You know, is it possibly when the sum is greater, when the whole, I'm sorry, when the whole is greater than the sum of the parts instantly, kind of when you look at a graph like the one behind you, where, you know, it kind of bridges the gap between the data points and the meaning, which is, of course, ultimately what you want, with the ability to display the whole. The whole is visible immediately. Does that make any sense to you at all?
I think it does. There is a sort of sweet spot. I think there isn't a recipe, just because that's where the kind of aesthetic dimension of design kind of kicks in a lot more. There's the sort of, what is the underlying data or finding, and, you know, what does that look like? What is it? How important is it? And then there's kind of, how does one choose to present it? And then how long do you expect the viewer to kind of be looking at the output? And there is a sort of sweet spot with certain kinds of data where the whole, like the picture, I'm gonna go this way, in the background is sort of, oh, look, you can see, you know, what it broadly looks like. The 20th century is a good time for reductions in mortality. And then there are also further details that repay kind of closer investigation. And so that's always a nice feeling when you can both kind of grasp it all at once, so to speak. And then also, if you look at it again, there's more there for you to investigate. And I think it's not just that there's a lot of data being shown. I mean, I think that one of the ways, for example, that a lot of data visualizations for people fail is that there's just too much information in them, and that you can't. The classic example is kind of the network hairball graph, you know, where it's like, here's 150,000 nodes and, you know, 20 million ties between them, and it's like, it does, you know, looks like something the cat threw up, and you can't really, the viewer can't really make anything of it except, wow, that's a lot of data, you know, and so you want to be able to, again, the decoding part is, oh, look, I can see this piece and I can see this piece, and each of those individual pieces, whether they're about the whole or a particular part, are things that you can legitimately pull out of the visualization and then sort of think about and make sense of.
Great, thank you.
Great. And do we have maybe one last question, recognizing that we're just about at time? Any, I guess with the advent of recent technologies, DALL-E, right, the large language model production of visualizations, you know, do you worry about the prospects of the future of visualizations, or and sort of misinformation being represented?
Sure, yeah. Well, I mean, those kinds of tools, they're very powerful and they're very interesting. I prefer to kind of have a solid grasp of understanding kind of how it is that they work, and be confident that they'll work the same way each time that I use them. The core virtues that we're after, doing things intelligently, reproducibly, and honestly, they don't go away, whatever the tool that we're using is. And so, insofar as those new tools can be used to further those goals, that's great. And if they don't, well, you know, that's a reason not to use them.
Yeah. Great. Well, again, thank you so much for joining us today. Check out his book, Data Visualization, A Practical Introduction. Yeah, please join me in thanking Dr. Kieran Healy for joining us.
Thanks very much.
We'll send out the recording for anyone who wants to, catch the full version if you came in later. So thank you. We hope you have a great day.